Good morning. This is now the 9th lecture in lattice Boltzmann methods. The counting is a little bit different from previous years. So today we continue with what we actually ended up last week, for those who watched the lecture of last week, and we learn, pretty, in my opinion, pretty important stuff concerning the multiple relaxation time. So now today we have a little bit an advanced lecture, but it's pretty important. I mean, I think you want to become scientists. So there is original work on exactly that topic, multiple relaxation time, lattice Boltzmann models in 3 dimensions by De Humier et al. In the Physical Transactions of the Royal Society in 2002. So you see it's already more than 20 years old. What they cover in there is the unweighted orthogonal MRT for 2 different lattices, namely the D3Q15 and the 19 velocity lattices. So this is a very important paper historically, and from the point of view how many citations it has. So if you do anything with lattice Boltzmann, you should be aware of this, and you should probably read it, also. But you should be aware, not only because it is old, but it is the correctness of what you read there is somehow in question, or it's after 20 years we can actually say, okay, we know that things there are wrong. So this paper has been also, it's cited over 2,000 times, but it has been criticized from different standpoints, and I think that some of the critique that has been put forward is probably not accurate. So some people say it's not actually original. This I do not agree. It's very original, but it makes several mistakes, and it actually does not show its complete procedure. So that is actually a paper in which you see a lot of magic numbers that somehow pop up that cannot be explained. This is also the reason why it's so often cited, because you cannot explain how the things came about, so you just have to cite this as the source, and actually these numbers are incorrect. Okay. So anyway, the question we are asking. Wait. I'm getting. So therefore, I think this is probably not in the book. What they don't tell you about MRT. Okay, so it's very good that you come to the lecture. So we have a starting point that is different from the one in this paper, namely, we take the tensor product lattice, so this is the D3Q, we are in 3 dimensions, so it's D3Q3 by the power of 3, so this will be D3Q27. And it's an historical fact that, tensor product lattice is actually the most logical way to start with. And now it's interesting that in this paper we have only 15 and 19 speeds. You could of course argue lesser degrees of freedom is more efficiency in a sense, of course, but they never, if you ask them, for example, de Humier, he would tell you, okay, I never tried this. So later Lamont and Dubois set up a lattice in MRT, lattice Boltzmann method for 27 speeds, at least theoretically, but it's never published actually. And now you can ask yourself, why is this the case? So what we find, so this is now the spoiler, what we find when we actually do this, so I implemented such a lattice, yeah, so I never used this in practice. The reason is because it doesn't work. Yeah, so the theory that they set up in this paper doesn't work with a D3Q27 lattice. So what you do as a scientist, you just say, okay, we never tried, right? But we want to know why this is the case, because actually you should think that taking more speeds make your model better and not worse. Yeah, so this is difficult to explain, and now today we are trying to do this. Okay, what we have to identify with these lattices is, of course, so we want to have many different relaxation times, and the question is, how many are there? How many independent relaxation times can now be identified or imposed? Say, okay, I write imposed because we imposed them. So, of course, there are as many relaxation times as you have moments, but there are, of course, symmetry constraints. So we're assuming isotropy, and this limits the number of relaxation times. So for this, we have to start with a grouping of the countable moments. And I remind you that in this paper, which is similar to the paper that we had discussed last time, they don't use countable moments, but they use moments that they identify with some sort of physical meaning. Okay, so we like countable raw moments, so we group now these countable raw moments. Yeah. So, and the first, I generate one group. So you could say there's also two groups, but I don't want to. I just group them. These are four of these. These are conserved moments, and so they have no relaxation time. So these are excluded from the search for relaxation rates. Yeah. So this is the zero one is of course the mass or the density. Yeah, depending on how you define it. And the others are the momenta, or sometimes they could also be the velocities if we define it in a different way. So 4 of them are conserved. So then we have 3 of the type M100 because we have 3 permutations, right? Of this guy. So then we have 2 M200 minus M020 and M200 minus 0, 0, 2. So for those who were there last time, yeah, not all of you. So we had this isolation in 2 dimensions. When we talked about this in 2 dimensions, there was of course only one of them, and here we have now 2, and this is because we have this isotropic part here again 0 plus m. So this, of course, there's only one of them. So these guys, as in 2D, they are the hydrodynamic moments. Okay, so technically, I'm not writing this here, but technically the conserved moments are also hydrodynamic moments, but they are not relaxed one. So they have a relaxation rate that is typically taken to be the one from the BGK. Yeah? So, and this here, the last one, this is the acoustic. Moment. And we give them, because we identify this with the pressure, we usually call this omega pressure. Yeah? And this is defining the bulk viscosity. Or setting the bulk viscosity, I'm reminding, as last time, I'm not going to define the bulk viscosity because the bulk viscosity in different parts of literature is defined in different ways, where there's actually just, something like, they are always defined in a similar way, but just a little bit different. The bulk viscosity adjusts all the definitions, but a little bit in different ways. So this is why I'm not defining it now here, and also it's not important for what we'll go to discuss. So now we have 10 moments, right? So we've defined 10 moments, and we have 27 populations. So there is another 17 obviously to come. And these are now our so-called ghosts. And now let us just name them like this. So we have third order ghosts, and we have different types of third order ghosts. This is why I write third order A. We have M, 1, 2, 0. So how many permutations does this moment have? 6. Because, okay, yeah, I'm just writing the same thing as last year. Okay, so it has 6 permutations. So at least you're reading with it. Okay, so yeah, for this big audience, I'm not preparing a completely new lecture. I hope you're not disappointed. Yeah. So okay, so we have 6 permutations of this. Then we have only 1 permutation of M111. Okay, so I don't need to ask you for permutations anymore, I'll see. And we have M220. Right? This is you can move the 0 around, right? So this means you get 3 permutations. And then we have fourth order B is M211, again with 3 permutations. So then we have fifth order guys. These are M221, also 3 permutations. And then we have 1/6 order. This is M222, and this is supposed to be 17 of them, if we sum them up, which I'm not going to do. So, now the question, so we can separate these guys like this, but now has each of these types each type its own relaxation rate, or is there more to it? Well, since you are reading it, you should know. So do we have one for each, or is there more to it?
One for each permutation.
No, not for each permutations, but we have 1, 2, 3, 4, 5, 6 types. Yeah? Does this mean we have what did I say? 1, 2, 3, 4, 5, 6. Does this mean we have 6 different relaxation rates, or is there more to it? There's more to it. Okay, so there's more to come, yeah? Okay. So what was your calculation? So it is not.
27, right?
No, we have, yes, so there are 17 moments, right? But due to isotropy, they cannot all have different rates. I mean, you can give them different rates, but then you don't have an isotropic condition, and so you will not have an isotropic simulation. So usually fluids are isotropic. There are exceptions when fluids are not isotropic, yeah, but in that case, so pure gas would be isotropic. So this means if you can make up these 6 groups, does this mean we get 6 relaxation rates because there are 6 such groups, or is there more to it? Okay, there should only be 6. So we get a few more, but we'll see why. So anyway, it's good that you are here, right? I mean, by comparison, yeah, let's look at not at the ghost moments, but at these guys. Because we said that these here, they are one type, right? And how many relaxation rates do they have? One? Okay, let me go back. Yeah, we have the sum of them and we have the difference of them. So then we have apparently 2, okay? So you see, already there is more to it, and this implies that down there's also more to it. So they are the same type, but they have 2 different rates. Because they can be rearranged because we have this guy, which basically is the pressure, and this is a so-called isotropic moment. And this has a different meaning from the others. So isotropic means invariant under rotation. Okay, so, and this takes us to rotation of moments. For rotation of the moments is very important to identify which different degrees of freedom in the modeling we have. So the lattice has 27 degrees of freedom, yeah, but the number of relaxation rates, this is the number of degrees of freedom for our modeling here, yeah, and this is identified by rotation of the moments, which was one of the subjects of my PhD thesis, and I now can announce that even though we are now looking in some things that I had in my PhD thesis, I also have to admit that not everything that I said there is correct. Because, you know, you learn over time, yeah? But let's go. So if you ever come around this paper, or you ever come around my PhD thesis, I mean, it's not necessarily that this is all incorrect, that we made mistakes, but some of the conclusions were not correct, because there are sometimes there's more to it than you see at the first glance, yeah? Okay, so let's look at our lattice velocities. No, the lattice velocity at the distribution for distributions. For the distribution Fij, so if you go if you go back to first and second lecture, yeah, we had the velocity of the particle xi as the vector xi. This is delta x by delta t into now for the lattice I, j, and k, right? Yeah. So, which means we can write this as I times unit vector x plus an j in unit vector y plus an k times the unit vector in z direction. And so formally we have to add here delta x by delta t. Which for reasons of brevity and other reasons we often just omit. So, now, what happens if we apply rotation? What happens if we apply rotation to this? So, suppose we have a different coordinate system which is rotated against our original coordinate system, and here we call this the unit vectors I, R, J, R, and K, R, yeah, they would be obtained by I times a rotation matrix multiplied with the vector x plus j rotation vector matrix times the unit vector in y plus k rotation matrix, sorry, times the unit vector in z. So what a rotation matrix is, you can look up in Wikipedia. I think it's not such a, I guess you learned it, but I always have to look the specific values up also. So for example, if we look at special rotations, for example, rotations around a specific axis, about, for example, the x, y, and z axis, then you just get, for example, we call this, because we're going to need this, so we call this Rx, by which we mean the rotation around the x-axis. So they just look like 1, 0, 0, 0, then cosine of the the angle that we rotate, and here we have sine, minus sine, alpha, and 0 sine, alpha, cosine, cosine alpha. So, and the rotation around the y-axis just distributes these things in a different way in our matrix. Okay, and let's look at the last one. Say we have cosine alpha minus sine alpha 0, sine alpha cosine alpha 0, 0, 0, 1, and I'm pretty hopeful that this is not new for you, right? Okay, so then this simply means that if you have a rotation around the x-axis, we get I, x, j, x, k, x is equal to I times r, rx into e, x, and j into r, x into e, y, and k, the rotation. So this is not a y, this is still an x, right? So we rotate all of them around x, and then we end up here with this. So, okay, so these are the operations that we need to do in order to identify the isotropic behavior of our moments. So let's just ask for a moment, why is the acoustic, so the pressure, the moment, acoustic, moment isotropic? Well, this is the case because the moment would, let's call it MP, yeah, so all of them together because it's the pressure, is M200 plus M02 plus M002. So we are going to compute this by summing over I, j, and k from -1 to 1. And we have I square plus j square plus k square. Yeah, so these are the moments. These are the kernels for the different countable moments, and they are summed up together. And they come to Fi, j, and k. So, and now when we rotate, when we do the rotation, of the coordinate system, and we do it with any proper rotation matrix, we would have I r square plus j r square plus k r square is equal to I square plus j square plus k square. So this is a little bit more involved computation. This is why I'm not showing it explicitly here, yeah. But this is what comes out. And this means that in any coordinate system where we take this moment, we always get the same moment, yeah? So this MP is invariant. We say it's invariant under rotation. So each coordinate system we are looking at, we always get the same pressure. Right? So we don't get the same velocity. If you rotate the velocity vector, you go from x to y, of course, but we always get the same pressure. Okay, so this can be separated out, and the same thing is not true for the hydrodynamic moment, where we look at some specifics. Hydrodynamic moment. So let's look at the moment M200 minus M020. This is equal to I, j, k equals to -1 to 1 is I square, not plus, I square minus. So I square comes from the first, and minus j square comes from the second, Fi, j, and k. So now we look at a specific rotation of this thing, namely, we see this is a moment that actually exists in the xy plane, right? And we look at the rotation of this guy with the around the vector that is orthogonal to this. So this would be the rotation around the z-axis. Yeah. So we rotate this thing around the z-axis. And what happens? Okay, I miswrote it here, so I try to correct it. So we have to now okay, so what happens if we rotate the vector I, our coordinate system? So we'll have we look at everything in the coordinate system with the z rotation, yeah. So when we multiply these vectors, so I briefly have to move upward, yeah. So what you get when you multiply this rotation matrix Z that I have up here with the units, with the normal vectors in the different directions, you get for the first vector you get the first column, for the second vector you get the second, on the third you get the third column, right? So that just means I can briefly write the cosine. So this is in the first column here, cosine sine alpha 0. Then we get the second column. This is minus sine alpha cosine alpha 0, and here we have k 0, 0, 1, where you see this is just identity for this, basically. Okay, so what we now want to know for that moment, we want to know what is I z, yeah, square. So we compute I z square, I z square, and this now will be I cosine alpha minus j sine alpha. So this and there's a 0 in the last line, and this guy here is squared. Yeah. So and this you can translate into I square cosine square alpha minus 2. So by binomische Formel. Also what is this? Binomial.
Distribution.
No, not distribution. Binomische Formel.
Yeah,
What is the word for binomische Formel in English?
binomial term.
Binomial term. Okay, good. See, what class is this? Sixth or something? I don't know. They don't teach you this in English in German. So the j sine square alpha. Okay. So the same thing we need for j square, because we also have j square. So j square. Now this is the second line in this equation here. This is I sine alpha plus j cosine alpha square. So this you can distribute as I square sine alpha. Now here comes a plus 2 ij cosine alpha sine alpha plus j square cosine alpha square cosine square alpha. Okay? So these guys come out, and what we now want to know is I z square minus j z square. Okay, so just put everything together, and what will come out is I square cosine square alpha minus sine square alpha minus 4 times ij sine alpha. Okay, I write it in the opposite direction than above, but what? Yeah, plus j square sine alpha square minus cosine square alpha. So so you see here's the same thing, yeah, and this can actually be rewritten if you. So we used to have this Russian book. What is? I even forgot its name. The Bronstein-Semmeldoyev. Yeah. So before we had Mathematica, we looked these things up in the book. Yeah. So then there is you see sine square minus cosine square. You can look this up in this book, or you can ask Wolfram Alpha, or what nowadays you do it this way probably. So we have twice the same thing, just with a different sign. So this is why I have I square j square, and this together, this gives you cosine 2 alpha. Yeah, so this translates to the cosine 2 alpha minus 4ij sine alpha cosine alpha. So what do we know now? What do we know now? We see that this here gives you the original moment with which we came in. So, and suppose our rotation angle is 0, then of course we get the original moment back. Yeah. So because we have cosine of 2, 0, which is 1, and here sine of 0 will be 0, so this will disappear. Yeah. So the other way around is we can also get this guy for particular angles to disappear, and then we end up only with this guy here, right? So, and what is this guy? This guy, of course, is M110, or M110 is the moment ijk equal to -1 to 1, and here we have ijfijk. So, this means that there is a particular rotation angle in this plane that turns your moment m200 minus m020 to the moment m110, right? And so this is why they have this the similarity, and the angle is a quarter pi. So the moment m200 minus m02, this maps to on m110 by rotation of alpha equal to quarter pi. So, does this mean that these guys have to relax with the same relaxation rate? Actually, I made a big fuss in my PhD thesis that this is the reason, and later I discovered there is more to it than just saying, okay, so they rotate on each other. So of course it is plausible to rotate them onto each other, and they have the same relaxation rate, but this is not strictly required. And the reason why this is not strictly required is a little bit more involved yet than what we had. So one thing that we have to know is how does the lattice map onto each other, onto itself. The lattice maps onto itself only after rotation of n pi half. So what does this mean? Let me draw it in 2 dimensions, because I cannot draw this in 3 dimensions properly. So now this is our lattice. So if you rotate this by pi half, so this is a pi half rotation, yeah, then the new lattice that we have, this will sit exactly on the old lattice, just the directions have changed, you know, their position. So, however, if we look at the rotations that of a quarter pi that we just had, so what happens with a quarter pi rotation? Okay, a quarter pi rotation, basically, I have to improvise a little bit. A quarter pi rotation will basically look like this. So this is a rotation by quarter pi. So, and you see here's a match, and here's no match. And this is, of course, you know, this has nothing to do with the physics behind it. This is purely the discretization. Yeah? So alpha is not necessarily n, I mean, it can be, but it's not necessarily n pi half. So this basically implies that numerically M110 and M200 minus M020, they can be in different sets. So they may have different relaxation rates actually. In the way we implement it, it's not the case that they have different relaxation rates, but there are models nowadays. So back then, 20 years ago, there were no such models. Nowadays, we have models that have different relaxation rates for these different directions. I come a little bit to an explanation for this later, but let's first look at the other ghosts, or at the ghosts, because this was not a ghost. So let's look at the ghost moments. The ghost moments. So for example, let's take the moment M210 minus M012. So this will have the definition f, the sum over ijk from minus 1 to 1 into I square minus k square into j, fijk, right? So I'm not writing everything, I'm just writing the result. We do a rotation about the, so what axis do we take? We take the y-axis, we rotate this guy around we rotate about the y-axis. We rotate about the y-axis. So, okay, we rotate about the y-axis because now the y-axis does not change, yeah? So because it is, this has a direction, yeah? It would be positive in the y direction, and we rotate around this, so we don't change this, and then we would have I y square minus k y square into j y. This actually is I squared minus k squared times j cosine 2 alpha minus 4 I j k cosine alpha sine alpha. So now what we identify is that there are now two terms, namely this one, which is the same that we had before, right? Yeah, so this is, so then it would be invariant under rotation, and here we have something that is related to a different moment. And one important thing that is missing here is there is no way that this maps onto I square plus k square, right? So there is no mapping, there's no rotational mapping no rotation maps M2 10 minus M0 12 onto M2 10 plus M0 12. And by the way, this has nothing to do with the lattice. Yeah, so that would be, even in completely isotropic case, there would be no such mapping. So what does this mean? So coming back to the question before, yeah, we said we have this group of moments, M2 10, yeah, where I said, is this one group, does this has one relaxation rate? Now we see we can isolate one case that cannot be mapped on the other case, right? So there would be, so this is a different group. However, okay, first, so they are in a different, not in a different group, but in a different set. So this is admissible from the perspective of isotropy to have different rates. So this moment alone, so this set here, we can split into two sets. However, there is one interesting fact, namely that M210 minus M012, they can map. So what is this moment? How is this moment called on which it maps? IJK, what is this moment? Now, which moment, which of the countable raw moments is this? One, yes. M111. So we can, by rotating this, yeah, we can map this into 111. So they can map onto each other. However, this requires a rotation by quarter pi, yeah, and not a rotation that maps the lattice on itself. And therefore, unfortunately, even though I claimed it differently in my PhD thesis, they are in different sets. Due to the discrete distributions. Yeah, so this is the rotation here would be p quarter, or not p half. Okay, so now we have three independent relaxation rates here for these guys. Three independent relaxation rates. Namely, we have M210 plus M012. So there are 3 permutations of this. And they come with the, say, the relaxation rate, because it's third order moment, I write it omega 3 plus, so you can give them different names. This is the name I just made up here. And M210 minus M012, of course, you will have the same 3 permutations. They have omega 3 minus, so this is completely physical. And then there is something artificial that comes from the lattice, namely that this guy is independent of the previous one. And this we give the omega 3. Okay. So what is the magic here? So relaxing M210 minus M012 and M111 with different rates would make the physics anisotropic. So actually, from a purely physical point of view, in nature, these things have to relax with the same relaxation rate. Yeah? So this would make it anisotropic. And now comes the caveat. In an isotropic velocity distribution, so the thing that we discovered, and only after working on this for a longer time, is that the lattice is anisotropic. Yeah, the lattice is anisotropic, and so then it does not necessarily make sense to make the relaxation pseudo-isotropic. Instead, what you actually can do is, by combining 2 things which are both anisotropic in the correct way, you can compensate at least part of the anisotropy from the one with making the other also anisotropic. Yeah? And this is the reason why on the lattice these 2 things are not necessarily relaxing with the same rate, and you actually get a better result. You can, it's pretty involved computation, but you can do the asymptotic analysis and see when we put these things into different rates, we get a better result. Okay? So this is something that actually was only discovered, I believe, in the last 10 years or so. So on an anisotropic, I just write it down for isotropic lattice. It is, probably not always, but say sometimes, just that you have an idea that something like this is possible, yeah? Sometimes possible. To compensate for anisotropies of the lattice with anisotropies of the relaxation rates and the equilibrium. in the relaxation rates and or equilibria. So this is actually how modern models actually work. Okay, let's briefly go to the forced moments. I know we are covering a lot, but then we are almost done with this. So we have the moment M220, M plus M202 plus M022. So if you look at this, you already can make a guess that this guy here is isotropic and can be isolated from the others. So this is I square J square plus I square K square plus J square K square Fij K. So I'm doing it a little bit quickly, but I hope that none of you has now problems identifying that this is the way this is computed. Yeah. And so for arbitrary rotations, what we'll find is that IR square J R, what am I writing? J R square plus I R square K R square plus J R square K R square is equal to I square J square plus I square K square plus J square K square, and therefore this is an isotropic moment. So, and then there are other guys, namely this M220 minus M202. So this is very similar to the ones that we already had. We do a rotation about the x-axis, because the x-axis is the odd man out of them, right? The x rotation about x-axis, and we get ix square j x squared minus k x square is equal to I square j square minus k square into cosine 2 alpha. Yeah, so it's pretty similar to what we had before. So we have the moment itself plus something that is that it can be turned into. It's 2 I square j k sine 2 alpha. So, and here we see that this can now be turned into the moment M211, right? By rotation. So, meaning that M220 minus M202, it does not map onto M220 plus M202 plus M022, but on M211 by rotation of alpha equal to quarter pi again, and because the lattice does not go onto itself by quarter pi around the x-axis, and because the lattice does not map on itself by that rotation, it can still rotate. It can still get a different relaxation rate here. So what we have then is here 3 independent rates So we have one M220 plus M202 plus M022, which we could, for example, call omega 4, let's call it omega 4 plus. Then we have M220 minus M202. So how many permutations are there? There's 3 of them, 3 permutations. So, and these guys we give the rate omega 4 minus, and then we have M211. This has also 3 permutations. And we give them the rate omega 211. So, with regard to the higher ghosts, we have M22 times, so there's not much space left, so we just give them all of them the rate omega 221, and then we have the 1/6 order guy that just gets omega 222. So all of this together gives us 10 relaxation rates. What am I writing? So this is the number of degrees of freedom in the modeling of the relaxation rates. Okay, so this is an important topic to cover, and now comes for the last half hour, comes the second important thing. So this is the identification. How many different degrees of freedom do we have in the first place, right? And now we have to get these things, now we have to assign different rates to these things, and before we do this, according to the original paper, we have to make the moments orthogonal to each other. So we don't work with this raw countable moments. By the way, the term raw does not mean that they are not orthogonal. The term raw means that they are in the lab frame of reference, so they are not shifted by the velocity in distinction to central moments. Okay, now they, according to the paper, will be made orthogonal. So we have to consider the orthogonality of moments. Okay, so here is really important. This is really an important topic, which I also think, if you look into the literature, you'll find it probably confusing. And the reason for this is that there was a lot of fighting going on, which in the last started to decay in the last, say, from 2014. There was actually the big crash as far as I can remember it, and then suddenly people started to settle to an agreement. So, but everything that was published before 2014 is completely confusing on that point, okay? So, and these papers, they are 2002, so they are much before this. So, the classical MRT uses unweighted orthogonality. I don't think that 2014 actually was already the paper. So this was the timing when the discussion was going on. That paper came a little bit later, and I think it's not settled everywhere. Yeah, it's not arrived everywhere, I believe. So, classical MRT uses unweighted orthogonality. What is this? So we have a moment, any moment. So the moments are usually given by, so originally they are given by integrals because we are on a lattice. We turn these integrals into sums, and these sums have kernels, and we call this kernel here phi ijk. So they are functions of the indices, and they are multiplied with fijk. So, and say we have a different moment, that's the moment m psi. This is the same sum over ijk. I'm not indicating where the sum is going to and from, because this is always true for any lattice. So then it's a psi ijk into fijk. So, and the orthogonality, the unweighted orthogonality, is given as when the sum ijk for that particular lattice of ij, the kernel ijk times psi ijk, if this is equal to 0. That this is the definition of orthogonality, right? So what we do. So and there's a very interesting thing. So people often try to derive things in 2D and then they generalize to 3D. And it turns out this is part of the problem in all of this, because the orthogonality has almost no effect in 2D, and this is something that we showed in the last lecture. So whether you take it orthogonal, not orthogonal, weighted orthogonal, anything doesn't change anything. So, however, if you do the same thing in 3D, you get you run into a big problem. You know, you get the million, I always tell the students, you get the €1,000,000 for proving that the Navier-Stokes equation has solutions only if you prove it in 3D. Yeah? If you prove it in 2D, which there's no money, right? Yeah? So you have to prove it in 3D. So there's a big difference. 3D behaves in a different way from 2D. Yeah? And this is something that we observe here. I'm probably not doing this in 20 minutes, but let's see. And okay, when we understood this, we thought about a specific example that would highlight this. Yeah. So if you wonder why we are taking this example, the example of a double shear wave. So this is nothing that comes up in nature, but we saw the thing is the following. We saw there is a theoretical problem with this orthogonality, or with the model, and we thought about one specific simulation problem that would highlight this, and this is this problem of the double shear wave experiment. So this has an analytical solution. Or it is an analytical solution of the Navier-Stokes equation in a periodic box. In a periodic box of the size L times delta x, so it does not have to have an extension. So it's three-dimensional, but its extent in the y direction is 0. Yeah? But the importance it still needs to be three-dimensional. Yeah? So it looks two-dimensional, but it's three-dimensional. The reason why it's three-dimensional is the following. We set ux to 0. We set uy to u0, L0 divided by L sine 2 pi x L cosine 4 pi. So this is the velocity in z in y direction. This varies in x and z. Yeah? So this is why it's three-dimensional. And this will decay over time with the viscosity in the exponent, e by the power of viscosity in the exponent times the time. And here we have the wave vectors, which is 2 pi L square plus 4/3 pi divided by L square. So this was just invented because it highlights this problem. So and then there is a velocity u set, which we also set to 0. So we have a plane in which the velocity varies and the velocity is going perpendicular to that plane. Okay. Okay, so what we do is, of course, initialize this thing, then we run it, then we measure the decay of this wave. Then from the measurement of the decay, we find the numerical decay, so the viscosity that would lead to that specific decay. Yeah? So up here we have a viscosity that we set, and we measure how fast is this decaying. And so we're doing a regression for this, and then we compute the error of the decay. So, and that's we call ER, so error for viscosity, and this is the physically set viscosity minus the numerical one divided by the physically set one. So, and this we repeat for different resolutions in diffusive scaling. Okay, so and now what is important, we set the hydrodynamic moments, the non-conserved, of course. Hydrodynamic moments, we set omega for them, we set them omega to the BGK variance, yeah? And all the ghost guys, all ghosts, we set them to 1 to see what happens. So what is going to happen? Let me see. Okay, so we get these things here as a result, and now I have to specify that MRT down here is the classical MRT with the orthogonal so this is the with the orthogonality. This here RM, this is raw moments. This is non-orthogonal. We are just not using orthogonality. So one thing that we observe here is that in most of these plots, it's not completely obvious everywhere. So I think here we still have it. Yeah, here we have MRT. in all of the others, so first of all, what we see is the error is large, so they all have the same convergence. It's just this does not have the same convergence in the beginning, but later they all have the same convergence. MRT has a large error compared also to the BGK. So BGK is always down here. So this, not everybody would like this, yeah, but is an order of magnitude. Is an order of magnitude. Is an order of magnitude more accurate, yeah. And the MRT, which was supposed to give you more stability, is only stable for the lowest viscosity and for the highest viscosity, and at lower viscosity, so these are different viscosities here. For lower viscosities, the MRT is going unstable. Yeah. So this is strange because we did all the exercise to get a more stable method than the BGK. And also we see that the error, so it's the least stable and the least accurate. Okay, so everything, as we say in Germany, everything was for the cat, yeah, for alles für die Katze, yeah, that we were learning here the last 2 weeks, and we should go back to BGK, you know. Now it would be very unfortunate to end the lecture here, because this is not true. Yeah? It is just that this was a botched model in the first place, and we know now, nowadays, we know how to do it correctly. But this requires some more exercise, so to speak. So, therefore, we'll have to continue the lecture now and look at what we learned in lecture 6, namely the asymptotic analysis. So this was lecture 6, of course. And we do this to second order. So to second order for any moment M, A, B, C. So now in lecture 6 it was 2-dimensional. Now we look at it as 3-dimensional part, yeah, because this is now being important. So for any moment to the second order M, A, B, C, this would be, according to what we derived in the previous lecture, the equilibrium of the same moment to the second order minus 1 over omega ABC, which is the relaxation rate associated with this specific moment, minus 1/2. Now this goes into dxm. Now A plus 1, now this is now a lot of writing here, BC. Now this here to first order plus the derivative in y, m, so bar, first order, A, B plus 1, C, plus the derivative in z, m, A, B, C plus 1 to first order and with bar and closing brackets. So now what we can do is we can look at the specific moment, and we look at the specific moment that makes the difference. Yeah? So, and of course, it's very unfortunate that we have only 10 minutes left because there's now a lot to say about this. So I choose a particular moment. Yeah? I choose a particular moment where I'm setting A equal to 2, B to 1, and C to 1. This gives me the moment M2, 1, 1, bar, and we look at this to second order. Now, spoiler, because I'm not going to discuss this in a lot of detail. As I said in the beginning, these guys, the French guys who invented the MRT, they did it for D3Q19. If you look at the D3Q19 lattice, this moment does not exist. Yeah? And this is why they were lucky, because we are now looking at what does this moment, if it exists. Okay? So, I mean, it does not exist means that it will always be zero by default, because we don't have the velocities that would make it up. Okay, let's look at this moment. So we have here now, of course, the equilibrium, second equilibrium, minus, say, okay, let's just say we relax this guy the way it is, and then we get dxm311. So you already know something about aliasing, so you'll know what this moment is. And 2, 1 plus the set. So which moment comes here? 2, 1, 2. Okay. Are you reading it, or you're thinking? You should think about it and not reading it. You're reading the book. So, okay, then, yeah, this is the same as last year, I know. Okay, so let's identify these guys. So the equilibrium we get from the factorization, right? So this is the meaning of the Maxwell equilibrium is that the different degrees of freedom factorize. So then we have M1001. So at least if I make a mistake, you should point it out, right? So that we have it later correctly on the recording. So in this we divide by the zero order square. So, and this turns out to be theta, which is theta is 1/3. Uy, so this is, last year I wrote this in a little bit different, but okay. And this into zero order for rho. Okay, so this is the equilibrium. Then we have the guy 311. Now you know about aliasing, right? So because we know about aliasing, this will be M111 to first order, and to first order this guy, because to third order it will be ux u times uy times uz, but this doesn't have any first order, so this is simply 0. And M212 to first order is equal to theta square rho 0 order uy first order, and then we have the other guy, of course, that looks the same way, is theta square rho 0, and that would be u set 1, obviously. Okay, so now when we put all of this into the equation, which I now call 9.1, so we have M20 to second order theta rho 0 uy first order u set first order minus 1 over omega 211 minus 1/2. This into theta square rho to 0 order, and here comes the derivative in y direction of z plus the z uy first order. Now, if you are familiar with lattice Boltzmann, you should actually immediately see what we have back here. Yeah? So, because this is nothing else than our shear stress. Yeah? And the shear stress we know from the from the hydrodynamic moment already. And this is also what is going to be the problem here. So, because if we look at the hydrodynamic moment, a specific one, A0, B1, and C1, then we have this guy is M011 bar to second order rho 0 uy 1 u z 1 minus 1 over omega. So this is now omega. Okay, I could actually wrote bgk. So this is the omega of the bgk minus 1/2 theta rho 0. And here comes the same thing. dy u z first order plus dz u y first order. So, which means we can solve for this, obviously, right? So we know that theta rho 0 dy u z first order plus dz uy to first order is equal to, let me see that I do it correctly, minus m011 to second order minus rho 0 uy first order uz first order, and all of this divided by, and here comes trouble, divided by bgk minus 1/2. So 1 divided by bgk minus 1/2. This is almost the viscosity, it's just missing a theta. Yeah? So we divide by viscosity. Okay, now why is this a problem? This is a problem if we put this into 9.1. So if we put this into 9.1, what comes out is M211 to second order is equal to the equilibrium still, or 0 u y first order u z first order, minus, now what we have here is 1 over omega, so how did I call them? Okay, I call them 211, minus 1 over 2 divided by 1 over omega bgk minus 1/2, and this 1 theta will remain here, and this goes into M011 to second order minus rho 0 uy1 uz1. So these guys, I mean, this here and this here would disappear if we look at central moments rather than Ra moments. Now, obviously, in BGK, what happens in BGK? In BGK means that all the rates are the same. So BGK would say that omega 211 is equal to omega BGK, right? So, and that would mean that 1 over omega 211 minus 1/2 divided by 1 over omega bgk minus 1/2, this is simply 1. So, what does MRT? MRT says that omega bgk, because we want to have small viscosity, so this is usually going towards small, towards 2, and the ghost moments, so which we have here now is omega 211, right? So these we now set to 1, yeah, because we want them to decay. So what is happening? What is happening is that 1 over omega 211 minus 1/2 divided by 1 over omega bgk minus 1/2, so this goes to infinity. And this is what we call nowadays, or this is my invention, so I call it that way. You can disagree or agree. This M21, this is a ghost moment, and this is the problem of a big ghost. So this is a big ghost. And it's a big ghost problem. Yeah? It's a big ghost problem because what you do is if you have a moderately large value for this hydrodynamic moment, it will make your ghost moment explode. So now the assumption is that ghost moments, they appear in the asymptotic analysis later, so we ignore them, but we cannot ignore them when they are very, very big. Yeah? So then they make trouble. Yeah? So this is a big ghost, it makes trouble. So we are out of time, but still, now I captured you, and now I just go on, yeah, whether you run away or not. So it's because this was not, yeah, this was not MRT. This was the raw moment, not the MRT moment. In the MRT we have orthogonality. So does orthogonality help us? We already know that it doesn't because we saw from the results that it crashed. Actually, this did not crash. Yeah? So this was better than MRT. So what is MRT doing though? Let's look at what we do when we have unweighted orthogonal MRT moments. So let me just call this for the time being, let me call this moment N211. Yeah? So this N211 made orthogonal looks like this. So you can look up, actually I looked this up in the lattice that Lallement and Dubois gave me for that purpose, yeah, and this looks like this. So you combine the actual first order moment with 3 times and subtract 2 times the second order moment, and this will make it unweighted orthogonal. So then this means for our, what does this mean for our for when we relax these guys? So we now have to do the substitution first in the equilibrium using the asymptotic analysis. So I hope this is not confusing now. So this moment, its equilibrium, is of course 3 times the equilibrium of the Ra countable moment, equilibrium 2. Now we have, I call the relaxation time now just ghost moment, yeah, because we are not relaxing the raw moments themselves, but we relax these combinations. This combination, so we have here the relaxation 1 over omega g, and this goes into rho 0, and I just write down the result. So we have, no, this is not correct. We have 3 times theta square minus 2 times theta into dy. So I've already computed this because I think otherwise it's getting boring. So this is what comes out of the asymptotic analysis. Now what happens if we plug in the hydrodynamic moment into the same thing? So we get M211, 3 times M211 equilibrium, square minus 2 M011 equilibrium to second order. And now comes the following. We get here 1 over omega g minus 1/2. So the important thing is we still have this guy, right? It has not been eliminated. Divide this by omega bgk minus 1/2, and we put in 3 theta minus So 3 theta minus 2, actually this guy here gives us a minus 1. And this multiplies with M011 to second order minus rho 0 u uy to first order and u z to first order. Okay, so in principle, we don't see that anything changed much other than the sign. Yeah? I mean, this will still be large, because we still divide by the viscosity. Still large. Only the sign changed. Okay, now I'm torturing you with the truth. Okay, so this is actually getting worse. So we have a big ghost that was positive. Now we get a big ghost that is negative. Okay, a few more lines. Now, once I put you so much full of information that you cannot get any more, I'm telling you the truth. So, because now I told you how it does not work, but there is a way it actually works. Yeah, we know a better way, and this is by using weighted orthogonality. Weighted orthogonal moments. We simply define a new moment, M211 equals to capital M211 minus theta M011. So I just define the moment like this. Now what is now happening if I do the asymptotic analysis of this guy? So we get again to second order with bar this moment. This gives us M211 equilibrium, second order minus theta M011 equilibrium to second order minus 1 over omega g minus 1/2. So now comes something very similar that we already had. So because we see both this guy and this guy. They both depend on the same derivatives. Yeah? And we had in the previous example where we tried to make it orthogonal the way they originally made it orthogonal, we see that we get some combinations here of, going back, we had a combination here, 3 theta square minus 2 theta. Yeah? And the problem with this is that this gives you minus 1 and not 0. Yeah? So what if we do the combination in such a way that simply this gives you 0? And now we have the case that simply this gives you 0. Yeah, so this still goes into u z first order plus z dz uy first order. So, because this guy gives you 0, what we end up with is if we, for example, so this guy itself gives you 0, but what would it mean? Is it meaningful that this guy disappears? So what actually happens to the moment M211 to second order itself? Because this is N211 equilibrium 211, no, sorry. Second order plus theta, so now this is the inversion of this, 011, 2, and this gives us M211 equilibrium, second order, plus theta, 1 over omega, because the other guy, so this guy does not contribute to the non-equilibrium part. Yeah, it does not contribute to the non-equilibrium part, so we have only the original BGK or part here. And because the viscosity is now small, this thing also is small, and this gives us indeed also a ghost, but this ghost is small. And actually, this is the basic idea behind, if I may do so, behind this cumulant model that we see at the bottom here, that gives us accurate results and high stability both together, even if we set the relaxation rates all to 1. Yeah? So we can construct a multiple relaxation time method with weighted orthogonality that solves all this problem. The cumulant lattice Boltzmann method does a few other things on top of this, which we'll cover in the last lecture of this series. Hopefully, because we still have one to go. Thank you for listening. Oops.